Today's goal is to prove trig identities. Trig identities are things that, well, identities in general are things that are always true, like x equals x, or 5 equals 5, or 3 to the 0 is 1, right? This is something that is absolutely true all the time. You're going to do this by simplifying expressions. Now, you've been simplifying expressions like for years. 5/10 is 1/2. Square root of 18 is the square root of 9 times 2, which is 3 root 2. It's handy to know that these two things, although they look quite different, are actually the same thing, so that, for example, if you and your neighbor are both doing a problem, you can check to see if you have the same answer. This is also helpful as a communication tool to know when you're on the same page and when you're not. So today we're going to prove some identities. We're assuming that this equation is true. We just need to manipulate one side of the equation until it looks like the other side of the equation. There doesn't appear to be a lot to do with 2, so let's work on the left-hand side. Now, one technique I like using is to rewrite everything in terms of sine and cosine, because sometimes that makes it really clear what you can cancel out. Tangent is sine over cosine, so that's easy. Cosecant is the reciprocal of sine. And so when we write it as a giant fraction, and we can put this cosine over 1, it makes it a little more clear. We can cancel out the cosines. And in fact, we can also cancel out the sines. And so you get 2 times 1 left over nothing. So just left over 1. 2 times 1 is 2. 2 over 1 is 2. So in fact, you just got 2 equals 2. Now, when you're done proving that something is true, mathematicians will sometimes use a square with everything filled in. They're usually using it on something much more sophisticated than this, but you can use either this square or you can use the expression QED, which is Latin for basically, I proved what I came to prove. It's sort of just a symbol you can use if you want to show, like, see, I did it, I'm done here. Okay, next example. We're going to prove this. Now, you can either work on the left-hand side or the right-hand side. I don't feel like there's a ton to be done on the left-hand side, so I'm just going to start with the right-hand side. I'm going to apply this same technique of demonstrating everything in terms of sine and cosine. You can use it or not. There will probably be a lot of guess and check, a lot of trial and error with these problems, and there are sometimes many ways to get to the right answer. So don't be intimidated when it takes you a while or you erase a lot and try new things. But one technique, this is just one of my personal favorites, is rewrite everything in terms of sine and cosine. And then take a look at this nasty piece over here. It's a fraction within a fraction. So I don't like working with fractions within fractions. Let's deal with that. I'm going to ignore the other terms for right now and see if I can get this term to clean up a little bit. So cosine of theta over sine of theta times sine of theta over 1. Oh, that's already nice. I can see that my sines cancel out, and so now I have 6 times the cosine of theta times 1 over cosine of theta minus cosine of theta over 1. Now, you guys know how much I love common denominators. It allows you to actually go ahead and subtract fractions. So let's get a common denominator here. This means you have 6 times the cosine of theta times 1 minus cosine squared theta. Cosine of theta times cosine of theta means you're squaring cosine. The abbreviation is to put that squared symbol here between cosine of theta, because cosine of theta squared means you're squaring the angle, not the cosine expression. So this is something different. Make sure that cosine squared theta, the squared part, is in the right spot. Okay, now at this point in time, you need to learn a new theorem. You guys know that the Pythagorean Theorem is just a squared plus b squared is c squared, right? And we know that if you're drawing an angle, and you're labeling its coordinate pair x, y, if this angle, we can draw a reference triangle. Let's assume it's in the unit circle, so it has a radius of 1. So then if we're applying the Pythagorean theorem to our reference triangle, then we know that x squared plus y squared is 1 squared. And x is the same thing as the cosine of theta, so we have cosine squared theta plus sine squared theta is 1 squared is 1. This is an identity you should memorize. You'll use it a whole lot. And often you'll use it in ways by rearranging. If you have like a binomial and one of the terms is 1 and one of the terms is either sine squared theta or cosine squared theta. For example, take a look at our numerator here. 1 minus cosine squared theta. Well, if I subtract cosine squared theta from both sides, I can see that sine squared theta is equal to 1 minus cosine squared theta. So that's sort of my hint when I see a binomial with 1 and sine squared theta or cosine squared theta. Sometimes I try to whip out this identity and rearrange the terms. So now I have 6 times the cosine of theta. I'm going to substitute. I know that 1 minus cosine squared theta is the same thing as sine squared theta over cosine of theta. And I'm sort of losing track of my goal here. I'm trying to show that this right-hand side of the equation is the same thing as 6 sine squared theta. Well, isn't that nice? My cosines will cancel out, and indeed, you just end up with 6 sine squared theta. So at the end of it, you have 6 sine squared theta is equal to 6 sine squared theta, which is obviously true. So go ahead and close it out. Okay, one more example for you today. Let's take a look at this equation. 7 times the cotangent squared theta over cosecant theta times secant squared theta is 7 times the tangent of theta times the cosine of theta times the cosecant squared theta. Woo, this one's a little bit messy. So it looks like there's stuff you could do on either side of the equation. Start wherever you wish. I'm going to start on the right-hand side. I'm going to rewrite everything in terms of sine and cosine. Cosecant squared theta is the reciprocal of sine squared theta, so we can just write it like that. Let's make this cosine into a fraction, just see if anything is nice. Oh, this is nice. My cosines cancel out. And then I've got sine theta over sine squared theta, so one of my sine thetas will cancel out. So this guy cancels with the squared bit, so you have 7 over sine of theta. Now, I don't feel like there's really much more that's obvious to do here, so maybe I need to work on the left-hand side for a while, and we'll meet in the middle. Okay, so I have on the left-hand side 7 times cosine squared theta over sine squared theta, that's my cotangent squared theta, over 1 over sine of theta, that's my cosecant theta. Secant squared theta is 1 over cosine squared theta. Ooh, this is messy. So we've got 7 times, let's take care of this guy first. So that would be cosine squared theta over sine squared theta times sine of theta over 1. And then we've got this 1 over cosine squared theta. Okay, now we can think about just multiplying it across, right, in the entire expression, actually including the 7. But I see my cosine squared thetas cancel out. Oh, the same thing happened here. A sine will cancel out with one of the sines of theta, so we get 7 over the sine of theta. Now, technically, I guess this is done because in both cases you have 7 over the sine of theta, but it's a little bit messy. Like by convention, we sort of like to start with working with one side and then just work with either the left-hand side of the equation or the right-hand side of the equation. So I'm actually going to rewrite it. Let's start with the right-hand side again. I'm just going to recopy sort of what I did, retrace my steps really. So if I worked in the right-hand side, I'm going to start exactly the same way. I'm going to keep this stuff above for scratch work. I have 7 times sine of theta over cosine theta times cosine theta times 1 over sine squared theta. And I will show that these guys canceled and this canceled with one of these guys. It didn't take a whole lot of effort to rewrite this step. So you get 7 over the sine of theta. And now I'm actually going to work backwards with the stuff I found over here. I have 7 sine of theta and I'm going to go backwards because this would not have been intuitive to me at all. I never would have thought, oh, well, you can rewrite 7 sine of theta as 7 times the cosine squared theta over the sine squared theta times sine of theta over 1 times 1 over cosine squared theta. But I can see that that's true. We can see that you would cancel this guy with this whole term with this whole term. We would see that you would cancel this term with the squared bit, so one of the sine thetas with one of the sine thetas. You can see why this is true. It just wouldn't have been obvious to go about it this way. And then let's keep going backwards up from my left-hand side. So this would be 7 cotangent squared theta times the sine of theta times the secant squared theta. And this, oops, I'm sorry. If we're working backwards, we're going to leave this 1 over cosine squared theta bit alone because that gave us the, looking back at my original problem. And this is in my original problem, so that's good news. And this is in the original left-hand side of the equation, so that is good news. And so let's just deal with this cotangent squared theta times sine of theta. This was 7 times, I'm trying to make it look like this. See, it's not an easy thing to do. Okay, we're trying to make it look like this guy. And so we have now cotangent squared theta times sine of theta. Oh, okay, so we like the cotangent squared, we just don't like the sine of theta. And so this would look like 7 times cotangent squared theta divided by 1 over sine of theta, right? Instead of multiplying by sine of theta, you could divide by its reciprocal. I don't know why you would do that, except if you were trying to prove that two things are the same. And now this looks like 7 times the cotangent squared theta over the cosecant of theta times secant squared theta, which is the very messy beginning. Now it's obvious that these two things are true because the left-hand side can be written identically as the right-hand side. And so this is the answer.